this.
What? I'm watching Office Hours because I don't know how to do physics. So yeah, sort of, but not.
Emma, that you were unmuted and you just told the whole room you don't know how to do physics, and I'm really sorry. Okay, so yeah, I think that's the housekeeping stuff. Let's go ahead and get started with this. I'm not able to share both the questions and the whiteboard, so if you want to take a second right now and open up the homework, I'll talk for about another minute and give you some time to pull up the homework. We're going to start with problem number 6. I'll still read them, and then I'll go ahead and sketch out the problem as I'm working on it. But if you'd like to have the actual text open, or you'd like to work on it while we're going through them, then go ahead and open up your homework now to problem number 6. And I'm just going to sort of teach the topics as we go. These problems will obviously get more complicated as we move through. So let's just start with the first one. This is chapter 3. Oh, they do tell us that's problem 3. Or maybe, I don't think y'all see the actual textbook question numbers. Okay, anyway, the question here, they tell us the x component of a vector is negative 29.6 meters. The y component is positive 54. And they're going to ask us for the magnitude and direction. So this is a task that you'll have to do a lot in this class when we deal with vector quantities. Hopefully, most of you are aware the idea of a vector is that it has a size and it has a direction. So the size we call a magnitude. I did not record any of those discussion sections, Jasmine, but if you want to stick around at the end, I have no problem going through problems 1 to 5. Okay, so yeah, so as I said, this is a task that you're gonna have to do quite a bit, where you have to find both the magnitude or the size of the vector and the angle between that vector and the positive x direction. Typically what I do when I'm sketching out a vector, when I have the components, is I like to draw them, tip to tail. That's the way that you're gonna add vectors graphically, they say. So it looks something like this. You'd have an x component here that's negative, and a y component that is positive. And we are going to place this on like a typical XY grid, where the right is positive x and up is positive y. And the resultant vector here is going to stretch from the tail of the x component to the tip of the y component. If we're dealing with a 2-dimensional vector, it looks something like that. And we'll show how to calculate that size. It's going to be, should be pretty straightforward. It should be something that you've done plenty of times without knowing you're exactly dealing with vectors. The other thing we're going to do is we're going to want to calculate the direction, and I'll talk about how to calculate the direction in just a little bit. But just to sort of plant this idea to begin with, we're always going to measure the direction off the positive x-axis. So that would be an angle, and we'll call that angle typically theta. So let's start with part A, where we're just calculating the magnitude. The way that we're going to calculate magnitudes in this class is going to be with a, why am I blanking out on the name of the Pythagorean theorem? So it's just a Pythagorean theorem, a squared plus b squared equals c squared. And the nice thing is that scales to 3 dimensions as well. We will have some 3-dimensional vectors, but for this one, it's only 2 dimensions. So just to get some practice here, the formal calculation will look something like this. The magnitude of A, sometimes you'll see A with a little arrow on top. The magnitude of A is equal to the square root of the x component squared plus the y component squared. This notation might be a little new to you, but the operation of adding things in quadrature, I'm sure you've done at some point in one of your math classes. For this problem here, we're just going to take the square root of the x component. The x component is negative. Of course, when we square a negative, it'll become positive, but you can go ahead and put the negative in there anyway, just for consistency. It does not want to take my dot because I have a smart thingy on. Okay. So negative 29.6 squared plus the y component, which is 54. And this is a nice equation that you can plug right into here. calculator. And if you do that with these numbers, you'll get 61.6. And the units here, since both the x and y components are in meters, the units carry over, and you also have meters here. So there's a free point on your homework. As I mentioned, the direction we always want to measure off of the positive x-axis. And what I'm going to do here is give you an equation that you can use with one little caveat that you have to be aware of. But when you are calculating the direction off the positive x-axis for a two-dimensional vector, the equation that you use comes from the definition of, oh no, please don't crash. Okay, good, we got it back. Tangent theta is equal to the opposite over the adjacent. The opposite, this can look a little funky, especially with a picture like we have here, where we're dealing in the second quadrant. But the opposite is always going to be the y, and the adjacent is always going to be the x. And so if we solve this by taking the arctan of both sides, you get that theta is equal to the inverse tangent of the y component over the x component. And as I mentioned, there's one caveat, and I think I'll go ahead and, well, we can actually use this problem to see what the caveat is. So I'm going to go ahead and flip the page here. Let me know if anyone needs me to go back when I'm done working through the problem. So for part B, we just want to calculate theta. As I mentioned, theta is the arctangent or the inverse tangent of a sub y over a sub x, which in this case is just going to be the y component of 54 over the x component of negative 29.6. Now I'm going to put this in red to indicate danger. If you plug this into your calculator, the answer that the calculator will give you is negative 61 degrees. If you're in degree mode, someone's going to do this in radian mode and get like a 2.1 or something, and they're going to have trouble. Make sure you're in degree mode when you're doing this calculation. Okay, now this is a danger. Why is this dangerous? Negative angles do exist in this class. A negative angle means that we rotate clockwise. So this would be a negative angle. And the corollary there, if you want it, is that counterclockwise is a positive angle. A negative 61 degrees, just think about this for just a second. 61 degrees is an acute angle. And if we're rotating clockwise from the positive x-axis, negative 61 should put you down here in the fourth quadrant. However, we know from our picture that we drew back here that our resultant vector should be somewhere in the second quadrant, not the fourth quadrant, but in the second quadrant. So the issue here is that your calculator does not know, when you enter in this expression here, your calculator does not know that the negative was on the bottom. So the rule is, and I will go ahead and type it up and see if this, sort of getting used to this. The rule is if the x component is negative, and we want to add 180 degrees. Did that work? Cool. Amber, yeah, thank you, Jocelyn. Yeah, you should be in degrees. You should always be in degrees in this class, as far as, I don't think there's ever going to be a case when you're going to want to switch to radians. So if you're in a math class where you're dealing with radians, make sure you make a note to switch to degrees when you go to do physics, especially before an exam. Okay, so here's our rule. If the x component is negative, and we're using our sort of shortcut equation up here, if the x component is negative, then we need to add 180 degrees to the answer. So now I'm going to use green here to indicate that we are writing down the correct answer here. Our correct answer would be the negative 61 that the calculator spits out, plus 180. And that's going to give us our correct answer of 119 degrees. Do you have any questions on this one? Other than the question about degree radians?
Oh, I drew it out. So, when we're doing tan, are we not finding the angle like between like I'm not sure how to describe this. Hold on, I have a picture drawn here. Maybe this will help. I don't know if you can see it. Sorry.
No, let me pull you up real quick. Yeah,
Okay.
okay. Oh, that's a good drawing. So which angle you were asking
I was
about?
thinking if we do tan, don't we find this smaller angle, but we want this big one, right?
Yeah, so in this class, whenever we're talking about direction, we're always looking for that big one off the positive x-axis.
Okay.
So the nice thing about using the formula that I've given you here is that this will always give you the angle off of the positive x-axis.
Okay.
So
Oh, so the tan
you
one
could
will
use
always.
your picture and use the absolute values and find that little angle, and then you could subtract it from 180 if you're comfortable with that. That's another way of doing it. That is how I did it usually when I was in this class. I just give out this equation because it's a kind of a one-stop shop. But that's a good question.
Okay. Yeah, I can see it because you adjusted it by 180, so I think I was about to say I think that like should put it back. I was just wondering because I drew it and I wasn't sure if I messed up the drawing.
Yeah, no. You had your drawing correct there. And
Oh,
if you were to find that angle, you would get a positive 61 if you were to follow your instinct there. And then you just have to convert that to be off the positive x-axis.
okay, thank you.
Yeah, all right. If everybody's good. Oh, let's see. What does the positive direction of x mean when solving a part B? That's a good question. So um, here is your set of axes. The right is positive x, the left is negative x, up is positive y, and down is negative y. And this will hold throughout the entire class. The x is going to be the horizontal and the y will be the vertical a lot. There's one exception, one type of problem that we'll get to in, I think, 2 weeks, where we'll tilt these axes. But for almost the entire class, right will be positive x, left will be negative x, up will be positive y, down will be negative y. And in general, when we're giving the direction of a vector in terms of an angle, that's always going to be measured off of the positive x direction. So that's why when they ask us in this problem, they ask us explicitly for the angle off the positive x direction, but if they don't explicitly say so, then that is to be assumed in the problem. All right. Tight. All right, let's go ahead on to the next question, question 7. So question 7 introduces a lot of notation. So I'm going to do, like a quick little 5-minute review. Anyone who has taken Calc 3 will know this stuff right off the top of the noggin. The first thing, let me just use one of these vectors that they give us to explain the first part, is that they give us vectors in this notation. A is equal to something like 8.9 I hat plus, whoops, not a T, plus 4.0 J hat. And you're doing it right now in Calc 3. Okay, cool. Yeah, so I hat and J hat, this is kind of a weird way of describing a vector, but essentially all that's going on here is that this is your x component and this is your y component. I hat and J hat are called unit vectors. They have length 1. None of that really means anything for you in this class. All you need to know is that whatever the coefficient is on the I hat, that's going to be your x component. Whatever the coefficient is on the J hat, that's going to be the y component. And sometimes you'll also have a third component that would be something like 3k hat. And for the astute observers in the room, you could probably guess that that's going to be your z component, whatever the coefficient is there. So it looks like an equation, but it's really, they could have just given you like an ordered pair. This is just how they give vectors in this class, and the I hat, J hat, K hat stuff is just like an antiquated notation from the 1800s. But that's how most vectors will be given to you. So this problem is just sort of getting used to that notation, and then also to these two operations. So I'm gonna probably just need a new whiteboard here. So the two operations, the first one is, let's do the dot product first. So the dot product is a special way of multiplying vectors together. Here's the thing. Since vectors have components, if I want to multiply them together, you kind of have to ask, like, what does that mean to multiply two vectors with directional components together? And the dot product and the cross product are two ways of doing that. So the dot product is probably the first one that you would instinctually try, which is if I want to multiply two vectors together, I just multiply their x's and their y's and their z's, right? So if you want to do a dot b, for instance, you would do ax times bx plus ay times by plus az times bz. That's it. Since each of these components is just the coefficient on that I hat, J hat, K hat, since it's just a scalar, when you multiply these together and add them all together, you're just going to end up with some number. So you should just get a numerical answer for this. And the other thing that I'll point out is that there's another side to this equation, which we will make use of in just a second. And that's that this scalar quantity here, sometimes called the scalar product, is equal to the magnitude of the vector A times the magnitude of the vector B times cosine of theta, where theta here is the angle between them. So again, we'll use that explicitly in just a second, and we'll talk a little bit more about how to utilize both sides of this equation to solve a problem. The other type of multiplication is something called the cross product, and this is actually going to be part A. So I'm going to go through, there are myriad ways to do a cross product. I'm going to show y'all how I do it. So let's start there. So if you have two vectors, let me go back to, say, this one. So I have my A vector here, and I could have another vector B. You probably don't need to write this down, but it would be something like bx I hat plus by j hat plus bz k hat, and allowing the first vector to be ax bx, sorry, ax ay az. So if I have these two vectors and I want to solve them in a cross product, what I do is I just take these coefficients. As I mentioned, the coefficients are the only important thing in this notation. So I'm going to take those coefficients and I'm going to put them into a matrix, and I'm going to stack them up. So the top row, it's going to be a 3 by 3 matrix. The top row is going to be I hat, J hat, and K hat. The middle row will be the A vector, just the numbers that are in front of the I hat, J hat, K hat, and the A vector. So just be like your AX, BX, oh no, AX, AY. I always want to do that. AX, AY, and AZ. And then the third row will be the components of the B vector. So BX, BY, and BZ. All right. And since we are in a matrix, we typically put these vertical lines on the side to indicate that it is a matrix. And here's the way that we're going to solve these. So the way we solve it with a matrix is you start in the upper left-hand corner, and you're going to go down and to the right, and you're going to multiply everything along that diagonal together. So the stuff that I've highlighted right here is going to be AY times BZ I hat And then I move one to the right and go along the diagonal. And you'll notice that this diagonal kind of clips through the wall here and comes back over on the left-hand side. So it's j hat az bx. Go ahead and add that. A, y, b, z, j hat. And then we move over to the right one more, and we're going to do k hat times ax times by. So plus ax by k hat. Now this is half the calculation. The cross product is quite a lengthy. I'll talk about Jaslyn. The example we're going to do is actually going to have no k values, but typically you just put a 0 there. That's if you really wanted to do it, but there's also a quicker way to do it. Where did AZ go? I did AY twice. Whoops. AZ should have been in the, this one right here should have been, I just read that wrong. Sorry, yeah, the subscripts here on the second one should have been AZ and BX. Thank you, Nina. Okay, so this is half of the calculation. The other half is we have to go in the other direction, down into the left. And when we go down into the left now, we're going to subtract. So I'm going to use red here. So start at I hat again, and we'll go down into the left. So we go through the I hat and then go to the AZBY. And we're going to, as I mentioned, subtract it. So we do minus AZBY I hat. Move over to the right and continue going down into the left. So J hat AX BZ. Subtract AX BZ J hat. And then the last term, our K hat term, will be K hat AY BX, or minus AY BX K hat. And then the last thing we could do, now that we have these two rows, is we can go ahead and combine like terms if we wish. And this will give you an equation that you can just use every time you're going to do a cross product. You're obviously not going to be doing like subscripts and stuff. You're generally just going to have numbers when you're doing these problems. So I wouldn't worry too much about the subscripts as long as you can get the shape of the matrix right. You're in good shape there. Okay, so combining like terms, combining my I hat terms together, I have AY BZ minus AZ BY. That's the I hat. And then combining the J hat terms together, I have, and I can just add them here, I have AZ BX minus AX BZ. That's the J hat. And then combining my K hat like terms, I have AX BY minus AY BX. No, I'm running out of space. And that will be the K hat. I'm so sorry. AYBX K hat there in the corner. So some of you may look at this. If you're a notation person, notation helps you. You'll notice that there's some symmetry. Like in the first term, you have Y and then Z and Y. That symmetry happens from, you can see it from a different way if you were to do the like minors. But in general, you should be good with either the shape of the matrix or using this equation. Everyone should be okay with doing one of those two. Now, Nina asked Jaslyn asked, what happens if there are no K hats? So the example that I'm about to do, there are no K hat, which means that your AZ and your BZ are both equal to 0. In that case, that means that the first term here would be 0 because there's a BZ and an AZ. And the second term would also be 0. Does everybody see that? Because you have, again, an AZ and a BZ in the second term. And so your resultant is just going to be in the y-hat direction. Now, a quick side note that might be of use to some people, especially if you're like a visual person. The reason for this is that the cross product is always going to give you a vector that is perpendicular to the two vectors that you input into the cross product. So if I have two vectors, such as in problem number 7, when I have a and b that have only x and y components, if I have two vectors that have only x and y components, those are going to be in the plane of the page, right, or in the plane of your screen. And the only perpendicular direction to that plane is going to be in the z direction, or pointing outward from your screen. And so that is the graphical reason, or the sort of physical spatial reason why you would end up with a cross product or with a perpendicular vector that is only in the k-hat direction. So let's go ahead and do that problem. And I'm trying to decide if I should do the whole, I think I should maybe, you know what, we're going to have more cross products that we're going to do in a second. So let's go ahead and for the sake of doing problem number 7, let's just use that little shortcut that I just talked about where the first two terms should go away. And so we just have ax by minus ay bx in the k-hat direction. Ax by minus by. Ax, what did I just say? Ax by minus ay bx. Sick. And that'll be in the k-hat. And this will be part A of problem number 7. So they just ask us for the magnitude, but of course we're going to automatically find the magnitude because there's only one component. So let's go ahead and plug in the values here for problem 7a. My values, my x component, I haven't gotten to problem 10 yet, Michael. The x component is 8.9, and the y component of my b is 2.4. The y component of my a vector is 4, and the x component of my b vector is 3.4. That's in the k-hat. And I'd go ahead and plug this probably directly into my calculator just like this, and I would get 7.8 in the k-hat. Now, as a note, as I said, they ask us for the magnitude of the cross product in part A, and the only way that they do that is just by having the vertical lines around the cross product definition. So the magnitude of A cross B is equal to the magnitude of 7.8 k-hat, and as I've already discussed several times, that's just going to be whatever the number is, whatever the coefficient is on the k-hat, so it would just be 7.8.
Are these vector cross products unitless, or do they have a unit?
So that's a good question. If the vectors themselves have units, then the answer would have whatever units the initial vector had. So if my components were given in meters, then my cross product would be in meters as well. For this problem, there are no units given, so these are just scalar numbers without units, and thus all the answers will be without units as well.
Okay, thank you. That makes sense. Yeah.
The flip side, so that's for the cross product. The flip side is that for the dot product, which we'll do right now, for the dot product, the units will always be, it will always be a unitless scalar.
Yeah, because I was thinking, I mean, if complete, right? Definitely.
Brian, I'm having a little difficulty with your audio chopping a little bit. If you do want to type a question in the chat, maybe.
Oh, that wasn't me. I muted.
Oh, okay. Maybe someone else just had a mic on. It had your screen highlighted. I couldn't tell. Okay. All right. So let's go ahead and do the part B here, which is the, oh no, the dot product or the scalar product. So this will be A dot B. And as I mentioned for this one, you just do ax times bx plus ay times by. And just for completion, I'll go ahead and put az times bz. Although for this problem, you'll have no z components. And so I just plug in, for mine, my x component of A is 8.9. My x component of B is 4.0. My y component of A is, that should be 2.4 rather. It doesn't, I guess everyone has different numbers, so it's not super important. But 2.4 and then 3.4, whatever. Let's see. My y component of A is 4. My y component of B is 2.4. And my z components for both are zeros. So that term will go to 0. And whatever this ugly lettering here, but if I go and plug this into the calculator, I would get 40. Again, no units here. Usually people don't have trouble with the dot product too much. So I'm going to go ahead and go to part C.
So this is the same as like the last problem, but instead of subtracting, we just added them.
Yeah, so it's let's see. So this is the dot product formula. If you just see this notation with the dot in between the vectors, then you just plug the components in like this. So you just multiply them together and add them up. If you see the cross product, I actually didn't write the cross product here on this slide, but if you see A cross B, like in part A of problem number 7, where you have the cross or like the times symbol in between them, then you need to do this whole long convoluted thing with this real crazy formula.
That's, I sure really enjoy seeing something like that. Yeah.
I don't know where the audio is coming from. Okay.
Okay.
Oh, it's Heba. Oh, I see. Okay. Thank you, Michael. All right. So part C is, well, let me go ahead and write down what the explicit thing that they're asking us for is. They have A plus B inside parentheses, and then they have it dotted with B. You're all good. So you could probably just take a wild guess at like how you're going to do this. Order of operations, PEMDAS, right? Inside the parentheses, you have 2 vectors that are added together. So we're probably just going to add our vectors together. And then outside the parentheses is a dot product. And you can probably assume that we would just dot the sum of these two with that B out there. So that is the most straightforward way to do this. You could do maybe some algebra with the dot product, maybe try to do some distribution or something, but the most straightforward way to do it is just to clear the parentheses and then do the dot product. So let's go ahead and clear the parentheses first. We'd have A plus B. No problem. I'm recording this and I'll probably send it out. If anyone does have to dip and wants to send me a message, I can't guarantee that the recording will like work. So your best bet is to stick around. But if anyone does need to dip, feel free to send me a message on Canvas and I'll try to send the recording to you. Okay, so A plus B is going to be very straightforward. You're just going to add the components together. So for my vectors, that's 8.9 plus 3.4 and the I hat. And then 4.0 plus 2.4 in the j hat. And yeah, I just sum those together. So 8.9 plus 3.4 is going to give me 12.3 in the I hat. And 4.0 plus 2.4 is 6.4 in the j hat. So if I sum 2 vectors together, I just sum them together component-wise, And I get a new vector, which also is given in the same component notation. Then the last thing I want to do is I want to dot this with B itself. So what that will give me, let's try a different color here. I just multiply now the x components together, 12.3 for my new x component right here. 12.3 times the x component of b. The x component of b was 3.4. And then I add that to my new y component, which we just found to be 6.4, multiplied by the y component of b, which has been 2.4 throughout. Plot this into the calculator, and we get 57. All right, I don't see anybody going off in the chat. Go ahead and do part D. For part D, they ask us a word problem at long last. They ask us for the component of A along the direction of B. I could talk at length about sort of the reasoning behind. Oh no, okay, good. I could talk for some time about like how to get to this reasoning. Let me just do like a quick little picture. Feel free to just like listen real quick. So let's say I have two vectors, A and B. I shouldn't have made them perpendicular. Let's say, yeah. Say I have two vectors, A and B. If I want the projection of A along the direction of B, then what I would need to do is I need to sort of like shine a light on A that would project it down onto B. And this would be the component of A along the direction of B. If you sort of see the shape of a right triangle here, your intuition is leading you in the right direction. What we could do is draw up a right triangle, and as long as we know the angle between A and B, then we could just use the cosine of that angle to find the component of A in the direction of B. Now, that is sort of the graphical explanation. All you really need to know is the dot product definition, which tells you that A dotted with B, there's another side to this equation. You have the ax bx plus ay by plus az bz, but the other side of the equation says that this is equal to the magnitude of A times the magnitude of B times cosine of theta, where cosine of theta is the angle between the two vectors, okay? And as I mentioned, if I wanted to find the component of A along the direction of B, I just need to find this red component, which would also be the magnitude of A times cosine of theta. Because it just comes from that right triangle, you just multiply A, whatever the size of A is, by the cosine of the angle between A and B, and you get some smaller component of A. You'll notice that that is on the right side of the equation, and I can isolate it. And by doing so, I end up with the magnitude of A times cosine of theta is equal to A dot B divided by the magnitude of B. All I've done here is divided both sides by the magnitude of B, just a little bit of algebra. And now, instead of having to do some complicated component-wise stuff, oh no. I hope, here, let me at least, whiteboard crashed. At the very least, let me put up what I just had, which is that the magnitude of A times cosine of theta is equal to A dot B over the magnitude of B. Okay, so yeah, so as I mentioned, instead of having to do some like crazy component-wise stuff to try and find the angle theta between two vectors, especially if I have three-dimensional vectors, that could be very complicated. All I need to do is find the dot product and then divide by the magnitude of b. So I've already found the dot product in part B. It's whatever your answer is to part B. So in my case, that's going to be 40. And then I just need to divide by the magnitude of b, which I haven't explicitly found yet, but it would just be the square root of the x squared plus the y squared. So for me, that's the square root of 3.4 squared plus 2.4 squared. And then you just plug this into the calculator, and for me, that would give 9.6. There are no units in this problem, but again, if your vectors do have units, then this answer would have whatever units the original vectors had. All right.
What are the bottom two values again?
Those come from my b vector. So you'll have a different b vector in your problem, but mine is 3.4 I hat plus 2.4 j hat. This is what my problem gave me in the red there. So if I want to find the magnitude of b, just as a reminder, then I just need to do the x component squared plus the y component squared underneath the square root. And my x component is whatever's in front of the I hat, the 3.4. So that's why I have 3.4 squared. And my y component is whatever is on the j hat, which is 2.4. And so that's why I have 2.4 squared. So I've just put this whole big calculation here. I just went ahead and put it under here because I wanted to find the magnitude of b. Have any other questions?
I had a question.
Yeah.
So on the homework on number 10, like on part F, it asks for the magnitude of the component of a vector perpendicular to the direction of b vector, but in the plane of a and b. And so I took like the scalar projection of a to b, but that was like what they asking e. So I'm not sure like what to do for like perpendicular to the direction of b. I'm not sure what that really means.
Yeah, well, are you okay to stick around until we get there?
Yeah.
We're going to try and build up to it. But you're
Okay.
you're asking the question in the right place. That means you're making the connection between these two problems. So that's good. We will get there. We will talk about that. Okay, so let's see. I'm trying to decide. Looking at problem 8, I was trying to decide how much time to spend on it. I do think that it has some value because they are three-dimensional vectors. But how about, do you all want to pick one of these are just kind of like drawn out problems and they're pretty similar. So if y'all want to put in the chat if you want to do part A, B, or C, I'll do one of those three. If there's one that part C, D, and E are all the same part. So if anyone has any preference between A, B, or C, if not, I'll just do probably part C because that's the most parts. Okay. I don't see any preference. So let's go ahead and do, problem 8. Problem 8C. So problem 8 gives us 3 vectors. Each of them, as I mentioned, have 3 dimensions. And for part C, we're asked to do this kind of compound calculation of A crossed with the vector sum of B and C. So as we did on the last problem, we need to clear the parentheses first. So let's go ahead and find our vector sum of B plus C. And in order to do this, all we need to do is add the components together. the corresponding I hat components for me are 0 for the x component of B plus 2 for the x component of C, that's in the I hat, plus the y component of B is 5, and the y component of C is -1. That's the j hat. That's a tall j. And then I have to add the z component of B, which is -3, and the z component of C, which is also -3 for me. And that's in the k hat. Combine these all together, and we have 2 I hat. 5 minus 1 gives us 4 j hat. And -3 plus -3 gives us -6 k hat. So this is our B plus C. No problem, see you later. This is B plus C, and then we want to finally evaluate the cross product with A. So I'll just go ahead and set up the matrix on the next page, and I'll put in the A there. I'm probably going to need to remember these. 2, 4, -6. 2, 4, -6. All right. So when I'm setting up my matrix, I do I, J, K for the first row. The second row will be the first vector, and it's important that you do this in the right order. So since A comes first in this expression, that needs to be the second row. B plus C comes second, so that needs to be the third row. Make sure that you keep these in order. If you flip the order, you'll flip the signs, and Wiley will not appreciate that. So, okay, so my A vector has components 0, 1, and -4. And my B plus C vector has components 2, 4, and -6. And now I need to find the determinant here. So starting with the I hat, we go down to the right. And that will give us 1 times -6 is -6. Put an equal sign here. So that's -6 I hat. J times -4 times 2 gives us -8 j hat. K times 0 times 4 gives us, we'll do plus 0 k hat. Of course, that's just going to be equal to 0, but just so you have it in your notes, there you go. Then we get back to I hat. Now we're going to go down to the left. I times -4 times +4. Now keep in mind here, we are subtracting. So I always start by putting a minus sign. Then I do -4 times 4, so that'll be -16 I hat. So my negative signs will cancel out there. Then I'll do minus, big minus j hat times 0 times -6. So that is 0 j hat. And then another minus here. K times 1 times 2 gives us 2 k hat. And then we go ahead and combine our like terms to get our solution. -6 I hat plus 16 I hat gives us 22 I hat. -8 j hat minus 0 j hat is just -8 j hat. 0 k hat minus 2 k hat is -2 k hat. And this will be your answers for, if I'm reading the problem correctly, for C, D, and E. Yeah, Amber, send me a message if you need it. Sure, yeah, so the -16 came from multiplying along the diagonal. When I was doing this red down and to the left, so I'm subtracting, and then -4 times 4 gives you -16. Cool. All right, in the interest of time then, if you have questions on the first two parts of that problem, feel free to send me a message in Canvas. Yeah, oh, okay, so this problem, let me read it real quick. It says, use the definition of the scalar product, A dot B equals AB cosine theta, and the component-wise one, AX BX plus AY BY plus AY ZBZ, to calculate the angle between two vectors. Now, we basically already made use of this. We could do a little bit of algebra at the top to sort of see how we would actually solve for this. But we know we have the two definitions. Well, we know that the A dot B, let's just do this. A dot B is equal to AB cosine theta, magnitude of A times magnitude of B times cosine theta. If I want to find the angle between two vectors, I just need to isolate theta in this expression. So I'll divide both sides by the magnitudes. So now you have the dot product divided by the magnitudes is equal to cosine theta. And then if I, oh, sorry, Michael, this is problem 9. So we just did, yeah, no problem. Okay, so yeah, and then we, you take the arc cosine and the inverse cosine of both sides, and you get that theta is equal to, the arc cosine of A dot B over the magnitude of A times the magnitude of B. All right, let's go ahead and see this actually in action. Now keep in mind, we're gonna have to calculate all three things that are inside of the parentheses. So we're gonna have to find a dot product, and then we're gonna have to find the magnitude of A, and we're gonna have to find the magnitude of B. And there's not really any way around doing that. So let's go ahead and do each of them with a new whiteboard here. My vectors are A is 5 I hat plus 5 J hat plus 5 K hat, and my B vector is 9 I hat plus 8 J hat plus 9 K hat. So you could probably, if you wanted to get a little bit of physical intuition here, you could probably look at these values and see that they're pretty close as far as the direction. So we should get an angle that's not too large. You also notice that these are in 3 dimensions, so there isn't a very straightforward way to just use trig to find the angle between them. So we really do have to use the dot product. Anyway, let's go ahead and calculate this. We'll just start by calculating the dot product. So A dot B is going to be equal to the x components multiplied together. So that'll be, I'm just going to sort of do this multiplication here. 5 times 9 is 45. That's 45 I hat. That should be a 5. 5 times 8 is 40 J hat. And then 5 times 9 is again 45 I hat. So that's one thing you have to calculate. And then I said we have to calculate the magnitude of each. And as I mentioned this at the beginning, but just to reiterate, we can still use the Pythagorean theorem, a squared plus b squared equals c squared. We just put another thing under the radical. So if I need to find the magnitude of a 3-dimensional vector, I just do all the components squared and added together. 5 squared plus 5 squared plus 5 squared. It scales like that, which is very helpful, and that's because their directions are orthogonal, whatever. Take linear algebra if you want to painstakingly prove why that is true. And this will give us, it'll be 5 root 3. I'm not gonna figure out what that is. And then the next thing we want is the magnitude of b. So we just do the same thing. We have 9, 8, and 9. So 9 squared plus 8 squared plus 9 squared will be what, 162 plus 64 is 166, 226. Did I do that right? Root 226. And again, as I suggest, don't plug this in. Oh, you know what? I just noticed that I did something very silly. For the dot product here, this should not have been a vector. Remember, that's a scalar product. So there's no components here. We just add those together. 45 plus 40 plus 45 gives us 130. Okay, and then as I said, we'll just hold on to these values and plug it all into our expression from the last page. So we wanted the dot product to be on the top, and then we want to divide by the product of the magnitudes. So that will give us that theta. Oh. Theta is equal to the inverse cosine of the dot product, 130, divided by 5 root 3 times square root of 226, or whatever yours are. And you can just plug that whole expression into your calculator and it'll come out. As I mentioned, we'd expect to have some small angle because of how similar these vectors are in direction. And we do, this one will just give us 3.1 degrees. Do you have any questions here before we go to the big one? Okay. All right. So problem number 10, just to read through it, they ask us what are the x component, y component, and z component of this vector r, which is given as a minus b plus c. They give us a, b, and c. So that part should be relatively straightforward. Part D, they ask us to find the angle between r and the positive z-axis. In part E, they ask us what the component of A is along the direction of B, which we've done. And then part F was the question that, I don't remember who, I think Michael maybe asked. What is the magnitude of the component of A perpendicular to the direction of B, but in the plane of A and B? So let's build up to that one, I guess. The first one is, I have some my numbers are all decimals, which it's just going to make this problem uglier. Yeah, let's do the first part, which is part A, B, and C. And I'm just going to make up some simpler looking vectors here. So for A, we'll call that 8i plus 4j minus 2k. For B, we'll call it negative 8i plus 8j plus 7k. And then for part C, or rather for vector C, we'll call this 8i, no, we probably need a different value. Let's call it 9i plus 3j plus 6k. Okay. And the first part, we get to do A, B, and C all at once here, is we need to calculate this new r vector. And they define the r vector as being A minus B plus C. So no dot product, no cross product here. We just combine or do the operations on each component, the I, J's, and K's. So for the X components, we need to do the same thing for each one, right? We take A, subtract B, and add C. So we do 8 minus -8, which will give us 16, and then add 9. So 16 plus 9 will give us 25 I hat. For the J component, we do 4 minus 8 gives us -4, plus 3 gives us -1 J hat, or just minus J hat. And then -2 minus 7 gives us -9, plus 6 gives us -3 K hat. And that will be your A, B, and C. So you get half the credit right there. Part D asks us to calculate the angle between this R vector that we found and the positive Z axis. Excuse me. So I've talked about finding the direction off of the positive x-axis. You could do some graphical stuff to find the direction off the positive z-axis if you wanted to. We can also use one of our tools. Remember, I think it was, what was it, the last problem, the problem before, I think it was, yeah, the last problem where they kind of walked us through using the dot product to find the angle between two vectors. So we know, I can actually just go right back to that one. We know this equation works universally. If I want to find the angle between any two vectors, I just need the dot product between those vectors and the magnitude of each. So the flip side of this is if I want to find the angle between my vector r and the positive z-axis, A could just be that r vector, and B, we could make any vector that points along the positive z-axis. So the easiest one for our B vector, the easiest one would just be to say that, well, let's see, we already use A, B, and C, so let's call it, what's another letter that we're not going to use? Yeah, Michael gets it, yeah. I guess, yeah, we could just call it the Z vector. So this would actually be, we'll just call it Z, but it would just be the vector 1 times k hat. This is the simplest vector that points in the Z direction. It just has length 1, so we know the magnitude right off the bat. And since it only has a k hat component, it's going to point right along the positive direction of the z-axis. If you got a quiz problem that said, what about the negative, the angle with the negative z-axis, what would you do? You'd just put a negative sign out in front. Or if they asked you to do it with the y-axis, you do 1 j hat. Or in part F, as we'll see, we have to do a little bit of a different direction. At any rate, we can go ahead and calculate that theta. Theta is going to be the cosine inverse, the arc cosine of A dot B over magnitude of A times magnitude of B. Now we've done a few of these, and Z is a very simple vector, so hopefully we can do some of this stuff in our head. A dot B, where we're dotting R hat, or sorry, the R vector with that Z vector. Since Z has no X or Y components, when we do the X component of R times the X component of Z, that's going to be 0. When we do the Y component of R times the Y component of Z, that's going to be 0. The only one that'll survive is this -3. So we have -3 times 1, and that's the entire value of the dot product. It's -3. And then on the bottom, we need the magnitude of A, which A here is the R vector. So the magnitude of that would be 25 squared plus -1 squared plus -3 squared. So 25 squared is 525, right? Oh, no. 625. I knew that. So that's 625 plus 1 plus 9. So that would be square root of 635. Not super important. You'll all have different numbers. And then the second one is we need the magnitude of b, which is our z vector right here. What is the magnitude of a vector with length 1 in one direction, right? Thank you, Michael. Yeah, that's just going to be a 1. All right. And then you'd plug this in and find the answer there. I just made up these numbers, so I'm not sure exactly what the value would be. Arc cosine of a small negative number, whatever that happens to be. I don't even have a calculator on me. So anyway, this will be some small negative number. I don't know if someone wants to do it, whatever. I think we get the procedure there. And yeah, okay. So we'll go ahead and, if there are no questions here, we'll go ahead and go to the next one. The next one is, again, a problem that we've done already before. They ask us for the component of A along the direction of B. Just as a reminder for this problem, this is the same problem that we've already done in problem 7D. So I'm just going to write as a note here that 10E, let's look at your solution for 7D. And those will be the same solutions. And then the last one here is problem 10F, the one everyone's been waiting for. 10F asks for the magnitude of the component of A perpendicular to the direction of B, but in the plane of A and B. So we've found the magnitude of the component of A that is parallel to the direction of B. In fact, that's part E, which is the same as 7D. You'd use a dot product to do it. But in this instance, they're asking for the magnitude of the component of A that is perpendicular. So when we found the component, you might remember that I sort of drew this picture where we have like A and B. And I said that if we wanted to find the component that is parallel to B, then I am projecting A downward onto B, and I need to find this little component right here. And this would be the, this ends up being the magnitude of A times cosine of theta, where theta is the angle between A and B. But now what they're asking us to do is they're asking us not to find the component of A in the direction of B. They're asking us to find the component of A in a very convoluted way. Essentially what they're asking us to do is to find the component of A that's perpendicular to B. That component right there. That's essentially what they're asking us to find. Good job, Michael. You answered your own question. I'm sorry that you had to wait until now to find it. But yeah, so it's just going to be the magnitude of A times the sine of theta. Now, here's the thing though. That may seem like a straightforward calculation. In fact, it would be, because you're going to find the angle at some point. Actually, you probably haven't calculated an angle. I don't believe you will have calculated an angle in part E. So the question is still how to find the angle. Now okay, there you go. So yeah, so the angle, one way to find the angle is to use the dot product definition that we already have, we've used however many times, where the theta is equal to the inverse cosine of A dot B over AB, the magnitudes. This is one way to do it. There's another way to do it though, that I think is worth mentioning because this is a very important relationship. So if you remember that the dot product is equal to AB cosine theta. So A dot B is equal to AB cos theta. There's a related relationship for the cross product, and that's that the magnitude of A cross B, because remember this is A cross B is a vector, but if we find the magnitude of the cross product, then that will be equal to the magnitude of A times the magnitude of B times sine of theta. So using this relationship right here, we can do something very similar to what we did with the dot product relationship already, and we can solve for A sine theta. And I guess I'll go ahead and do the problem that way. So that would be, by the way, it would give us A sine theta is equal to magnitude of A cross B divided by the magnitude of B. So let's go ahead and solve the problem this way. We just need to do A cross B. So we'll have I, J, K. I think it helps to see another cross product done probably for most people. I made up some fake numbers somewhere, right? For A and B. Where was I? 8, 4, negative 2, negative 8, 8, 7. 8, 4, negative 2. 8, 4, negative 2. And negative 8, 8, 7. Find the determinant here. All right, and let's practice our cross producting. Starting with I hat, we go down and to the right. 4 times 7 gives us 28 I hat. Then J hat times negative 2 times negative 8 gives us plus 16 J hat. And then K hat times 8 gives us plus 64 K hat. And then we will go down and to the left, I times negative 2 times 8. Keep in mind here we're subtracting, subtracting every time. So we subtract negative 2 times 8, so negative 16 I hat, minus J times 8 times 7, which is 54 J hat, minus K times 4 times negative 8, which is negative 32 K hat. And now we go ahead and combine our like terms. 28 minus negative 16 is going to give us 44. 44 I hat. 16 minus 54 will give us negative 38 J hat. And 64 minus negative 32 gives us plus 96 K hat. All right, very, very large numbers, which I regret immediately because we need to find a magnitude. This formula here asked us for the magnitude of A cross B divided by the magnitude of B. So the magnitude of the cross product will be the square root of 44 squared. I should do plus, negative 38 squared plus 96 squared. Thank you, Michael. 112.23, call it. So that is the magnitude of our cross product. the other thing that we needed to find was the magnitude of our B vector. Our B vector was the -887. Let's see if I can fit this in here. The magnitude, oh, let's just go to the next page. -887, okay. So the magnitude of B is just equal to the square root of -8 squared plus 8 squared plus 7 squared yeah, you can, Tiffany. I mean, we're basically done here. We just need to divide these two numbers. But yeah, if anyone needs the recording, please feel free to message. What do we get here? About 13.3. All right, and then just the very last thing is to go back to that solution that we had a few pages ago, which was that a sine, no, don't crash. A sine of theta is equal to the magnitude of the cross product divided by the magnitude of B, which is the 112.23 over 13.3. And that's just some number 8.44. And of course, as I mentioned, the other way to do this is if you want to use the dot product definition to find theta, you could have just found the magnitude of A and multiplied by the sine of theta. And then, yeah, and that's it. So if anyone has any questions, also, if there's anyone who has decided to stick around to talk about the first 5 problems that we went over in discussion, please feel free to stick around. But first, if there are any questions on these last 5 problems that we just went over, please let me know. I'm going to go ahead and stop the recording here.